Hi, welcome to our Milestone 3 presentation. We are Team 4. My name is Sai, and I'm here with my teammates Robin and Marta. Our research question, which we stated before, is to predict the amount of greenhouse gas emissions per capita for a country in 1 year based on historical data of multiple environmental indicators and features. The first type of machine learning model that we explored in this milestone was the support vector regression. Given that our dependent variable, greenhouse gas emissions per capita, is a continuous feature, we chose to go with a regression instead of a classification. First steps for this is training and feature scaling. Our initial run of the model failed after running continuously for 20 minutes before we had to stop it. And research found that scaling would help improve the situation as it can optimize the algorithm used by the SVR model and allow it to converge faster and thereby train faster. So we used the standard scalar method to allow for the SVR model to run smoothly. First model that we created was a linear kernel. After predicting the model on the testing set, we calculated the root mean squared error, which is a value to determine the predictive accuracy of the model, where lower values correspond to a higher accuracy. The linear kernel resulted in an RMSE of 1.902. We repeated this analysis with three other nonlinear kernels offered by the SVR package, the radial basis function, sigmoid, and polynomial kernels. The best results was from the radial basis function kernel, which had an RMSE as low as 1.34, which is lower than linear. The other two, however, resulted in RMSE rates that were higher than the linear kernel, as high as 5.41 and 2.54, meaning that they performed much worse. The next model that we explored was the neural network. Using the TensorFlow Keras Python API, we created it. The first step was to feature scale and normalize the input variables to a 0 to 1 range, which we did using the min-max scalar method. Then we created multiple configurations which correspond to different neural network architectures with a varying number of hidden layers and number of neurons per layer. We created a total of 5 different architectures. We also created a list of 5 different activation functions, and then used a double for loop to iterate through each type of network architecture and had it run for each type of activation function for a total of 25 different combinations that we tested to be able to see which combination would yield in the best predictive accuracy. An obvious trend was found in that as the number of hidden layers and the number of neurons per layer increased, the predictive accuracy also increased, as you can see in these two tables, where the root mean square error rate goes down, while the correlation coefficient between the prediction and the test values goes up as the number of neurons and layers goes up. The overall best neural network was the model with 3 hidden layers and used a scaled exponential linear unit activation function. The RMSE rate was as low as 2.53, and the correlation coefficient was as high as 89.65% for this one. You can see the plot of this diagram here, where it starts with 15 input variables, followed by the 3 hidden layers, and finally the single output layer.
For this portion of the presentation, we'll explore different clustering methods. And the feature that was explored in this case was the population versus the GHG emissions per capita. The first algorithm that we explored is partitional clustering, which divides the dataset into clusters where each data point belongs to exactly one cluster. And one of the most popular algorithms is the k-means, which we've explored in this particular case. So as mentioned, each point belongs to exactly one cluster, and then the algorithm begins by selecting the preferred value for k, which will be the set number of clusters once the dataset has been partitioned. So after repeating this process several times, it was determined that the best value for k was 3, and a common method to verify the best value is through the elbow curve, which will be shown in the next slide. As we can see here on the left, we have the elbow curve, and we can see that at 3 we have the elbow point, which indicates that as the number of clusters increase, the whole model will be converging. And then on the right, we see the different clusters, and we can see 3 distinct clusters, and the X's indicate the centroids for these clusters. Next, we'll have a look at the hierarchical cluster. The hierarchical cluster organizes the dataset into tree-like structures known as dendrograms. The leaves of the tree represent the individual data points, and the branches represent the clusters of the various sizes. For our chosen cluster, we have three distinct branches, which are also our clusters, and the number of elements per cluster are 16, 320, and 144, respectively. Next, we'll explore the density-based clustering algorithm. Density-based clustering is a technique that identifies clusters based on density of the data points in the feature space. And unlike partitioning or hierarchical clustering, density-based clustering does not require a specific number of clusters beforehand and can discover the clusters of arbitrary shapes and sizes. For this density-based clustering, we use the dbScan algorithm. The dbScan uses two parameters, epsilon, which is the distance threshold that defines the neighborhood of a data point, and the min points, which is the minimum number of points required to form a dense region. For our given dataset, we chose the epsilon value of 0.5 and the dense region to be at least 5 sample points. The following cluster was generated using 1,000 sample tries and 42 random states. And to the right, we can see our dbScan clustering with 4 distinct clusters, and the purple dots indicate the center points. Now let's have a look at the comparative analysis. The classification task method that was used for this comparative analysis was the decision tree model, which was implemented in Milestone 2. After running the caret package in Python, it was possible to obtain a list of all of the different models and how well they performed in comparison to one another. In question 1 of this milestone, we used the SVM model with a linear kernel, which performed relatively well with a prediction rate of 81%. In question 2 of milestone 3, we implemented the neural networks, which performed significantly better with a prediction accuracy of 89%. Lastly, we compared it to question 3 of milestone 2, which made use of decision trees and random forests. These two models performed the best with an accuracy of 100% as shown in the figure below. Now let's have a look at the different cross-validation techniques. For our particular dataset, we decided to use the 5-fold cross-validation, the 10-fold cross-validation, and the leave-out cross-validation. These 3 cross-validation techniques proved to work the best with our target feature, which was the GHG emissions class definer. So starting off with the 5-fold cross-validation technique, the model is trained and evaluated 5 times, and each time a different fold is held out for the validation while the remaining 4 folds were used for training. This technique used the least computational time since it required less training and evaluation of the models. Secondly, we had the 10-fold cross-validation. In the 10-fold cross-validation, the model is trained and evaluated 10 times, and each time a different fold is held out for validation while the remaining 9 folds were remained in training. With the 10-fold cross-validation, there's more statistical stability in estimating the model's performance compared to the 5-fold. Then lastly, we had the leave one out cross-validation. For each training iteration, a model is trained using all the data points except for one which is being left out. The model is then evaluated on that single point that was left out. This gives an estimate for how well the model generalizes for unseen data points. Based on all 3 cross-validation techniques, the decision tree classifier was the best at determining our GHG emission classes.
When performing feature selection methods on our previously created models, we began with our linear regression model. We performed a filter method to test the impact of this type of feature selection on our model. We began by rerunning our original model for comparison and then used the f-regression package on our training set. We were able to plot the p-value results for all of our features and found that all features, aside from 2, produced a p-value less than 0.05. Based on these results, we identified the values in the top 30% of these results, which resulted in a list of features containing GDP per capita, access to electricity percent of rural population with access to electricity percent of total population, access to electricity percent of urban population with access, and total final energy consumption per capita. After applying only these selected features to our model, we got training and testing scores of 0.53 and 0.41 respectively, indicating a decrease in our model accuracy scores. We also got a correlation coefficient of 0.65 and a p-value of about 1.33 e to the negative 15, indicating a decrease in the correlation coefficient and increase in the p-value. Next, we used our previously created random forest classifier model to implement a wrapper method of feature selection. We avoided overfitting using a threefold cross-validation. We found that the accuracy of our model remained the same, however our features of importance changed slightly, as well as their importance scores. Our features of importance were agricultural land percent of land area, population total, total electricity output per capita, and total final energy consumption per capita, eliminating GHG emissions per capita. The importance values for total final energy consumption and total electricity output were very similar at about 0.38. The next model we used was our previously created logistic regression model to implement an embedded method. We used lasso regression to determine which coefficients were not equal to 0. We ended up with two selected features: energy intensity level of primary energy and renewable energy share of TFEC. When rerunning the model with just these features, we found that our model accuracy remained the same. When it came to ethical issues related to our project, we had to think about our project as a whole, reflecting on issues throughout data collection, manipulation, and model evaluation. When we found that our original dataset contained features that could not be directly compared between countries, we decided to discard that dataset and found a new one with the original features as well as population totals. As a result, we were able to normalize our features using population and make them more representative. We have also recognized that our data is very broad in scope, as broader data is easier to find a lot of information for. Our data will not be able to reflect in-depth practices within each country and will not allow us to make insights across industries, sectors, or various identifying demographics. We also noticed that some of our models were left with limited ranges of features following feature selection. While this can be useful in improving model accuracy, we found that it removed features that added context to other features in our dataset. For example, our logistic regression model ended up with the features energy intensity level of primary energy and renewable energy share of TFEC, but was no longer taking into account the access to electricity values that would provide these features
with added context.
And that is all for our presentation. Thanks for listening.